Monolithic PHP modules often reach a breaking point where the rigid connections between components begin to fracture under the weight of new feature requests. The difficulty lies in the traditional reliance on scattered global functions and untyped arrays. Handlers frequently mix raw database queries with core business logic, creating an environment where a change in one area causes unintended side effects elsewhere. Without architectural separation, unit testing is effectively blocked. Implementing modern features becomes a process of navigating through tightly coupled legacy code rather than building new functionality. The XMF architecture provides a tiered structure to resolve this: core, extended, infrastructure, and orchestration. This framework allows for the incremental modernization of legacy components without requiring a complete rewrite of the existing module. Modernization begins with the dependency injection layer. By moving service management to this tier, we can begin to isolate components from the global state. In the second phase, entity structures are updated. PHP 8.4 property hooks provide strict type safety, while traits allow for modular behavior composition instead of deep inheritance chains. The final tiers deploy a decoupled event bus. This system manages side effects and asynchronous jobs, removing them from the primary database handler. This tiered approach shifts logic from manual, brittle blocks into declarative code. This ensures the architecture itself maintains the integrity of the module as it scales. To eliminate global state, we replace scattered database factory calls with a central dependency injection container. A dependency injection container is a tool that manages the instantiation and delivery of objects, ensuring that each component receives its required dependencies from a single source. This blogmodule.boot method acts as the single source of truth for the module. It centralizes the registration of infrastructure, event systems, and repositories using a singleton pattern. By using the container for registration, we enable lazy loading. The database connection and other services are not instantiated until a component specifically requests them. We also register the config manager within the Bootstrap to define type-safe configuration schemas. This allows us to enforce that a setting like posts per page is always treated as an integer with a reliable default value. Validating these schemas at startup prevents the application from processing incorrect configuration data, a common issue when using legacy array lookups. The boot sequence further utilizes the convention registry to standardize table names, templates, and constants across the module. Centralizing the module setup in a container removes the need for repetitive boilerplate. It creates an explicit dependency graph that makes the entire module more predictable and easier to test. Modern entity design requires moving away from deep inheritance trees toward flexible composition. Composing entities with traits allows us to add specific behaviors, such as SEO metadata or audit logging, horizontally. A trait in PHP is a mechanism that allows for code reuse by inserting methods into classes without requiring a common parent. We modernize data structures by using PHP 8.4 property hooks. This provides a type-safe, validated layer that sits over the legacy untyped data storage. Because these property hooks wrap existing data setting methods, they maintain full backward compatibility with the legacy database layer. This design ensures that essential logic, like tracking modified fields, triggers automatically whenever a property is updated. We can also apply PHP 8 attributes to define machine-readable column metadata directly on these entity properties. Other components in the framework read these attributes to generate user interfaces and database tables automatically. Using attributes removes the manual work of building HTML forms or writing custom code to capture and validate form state. This combination of traits and property hooks provides a modern, type-safe interface while retaining the original storage mechanics. Moving from legacy database querying means replacing string-based criteria and complex nested arrays with more reliable structures. We replace legacy criteria with a fluent query builder. This provides type safety and IDE autocomplete, reducing the risk of syntax errors in database queries. This logic is centralized within the repository pattern. A repository is a structural pattern that abstracts data access, allowing the application to interact with entities as if they were part of an in-memory collection. The repository provides a consistent API for all persistence tasks, preventing direct database handler calls from being scattered throughout the application's controllers. We use lifecycle hooks within the repository to intercept data immediately before it is saved to the database. These hooks can be used to automatically set timestamps or create versioning snapshots without involving the main business logic. Since the XMF framework wraps existing handlers securely, you can migrate legacy code to this repository structure incrementally. This isolates the database operations, resulting in persistence that is predictable and standardized across the entire module. A core principle of this architecture is that database handlers should never trigger emails, notifications, or clear caches directly. Instead, the repository dispatches a domain event through a PSR-14 event bus when an entity is successfully saved, alerting other parts of the system. Independent listeners react to these events, performing tasks without interfering with the primary save operation. This allows one listener to handle cache invalidation while remaining completely unaware of how the post was actually published. We must also prevent computationally heavy tasks, like bulk notifications or image processing, from slowing down the user's experience. For these tasks, we use listeners that intercept the event and move the workload into an asynchronous queue for background processing. These background tasks are defined using a specific queued job attribute within the class. The event bus passes these jobs to the module's queue runner for execution. This ensures the initial HTTP request is completed quickly, as it no longer has to wait for side effects to finish. Routing side effects through an event bus isolates the synchronous handler from these asynchronous workflows, increasing the overall resilience of the module. This layered architecture enables deep testability across the entire module. Because we use dependency injection, Tier 1 services are kept separate from the application logic. We can use the container to replace real services, such as the database connection, with mock versions during testing. This allows for the execution of unit tests on individual components without needing a full web server or a live database. We can also run comprehensive integration tests to confirm the entire persistence cycle works correctly together under realistic conditions. Our data flows from the central container into strongly typed entities, then moves through the repository layer to the event bus. From there, the data passes through the event bus and enters the asynchronous queue box for background processing. The combination of a central container, property hooks, and isolated side effects allow legacy modules to operate with the reliability of modern software.